Hello, I'm Edward Tarte, math teacher. This is one in a series of solution videos for some of my math challenges. This challenge is my Counterweights math challenge, and here's how I presented that challenge in the original video. This represents a balance scale. Suppose that in former times a druggist has a scale like this, which he uses to measure weights of medicine in increments of 1 gram. 1 gram, 2 grams, 3 grams, 4 grams, 5 grams, and so on. And in order to do this on his balance scale, he has a set of 5 counterweights. For example, this represents a counterweight of 1 gram. If he has this counterweight, he could put it on one pan of the scale and balance it with 1 gram of medicine in the other pan. Suppose that he has exactly 5 counterweights, and they are such that he can measure out increments of 1 gram, 1, 2, 3, 4, 5, 6, and so on, up to the highest possible total. I have 2 questions. What weights should these 5 counterweights be? And what is the highest possible total number of grams that he can measure using the 5 counterweights? Here's my solution. Several of the respondents reasoned very naturally in this way. We have to have a 1, and we will also have to have a 2. We can get 3 by adding them, 1 plus 2. We will then have to have a 4. That will allow us to get also 5 from 4 plus 1, 6 from 4 plus 2, and 7 from 4 plus 2 plus 1. So next we need an 8. And then we can get 8 plus 1 is 9, 8 plus 2 is 10, 8 plus 2 plus 1 is 11, 8 plus 4 is 12, 8 plus 4 plus 1 is 13, 8 plus 4 plus 2 is 14, 8 plus 4 plus 2 plus 1 is 15. So now we need 16. And then we can get, as you can readily determine, from 16 through 31. That's what all those numbers add up to. And so this is a natural solution. However, this solution assumes that the weights are always put entirely in one pan and the medicine in the other pan. But nothing that I said in the statement of the challenge rules out the possibility that weights could be put in both pans and the medicine in one pan. If weights can be put in both pans, we have to include subtracting as well as adding. So a correct solution to the challenge must involve that concept. How will we do it? We will have to start with a 1. Do we need a 2? No, because we can have for our next weight a 3, and we get 2 by 3 minus 1. This also gives us 3 and 4. It does not give us 5. To get 5, we need 4 plus 5, which is 9. That way we can get 5 by 9 minus 4 and by 9 minus 3, 9 minus 2, and 9 minus 1, numbers which we already know about, and then 9 alone, and then 9 plus 1, 2, 3, and 4, numbers which we already know about. We can get up to this total, 13. To get 14, we will add 13 and 14 and get 27 as our next weight. That allows us to get 14 by 27 minus the previous ones, adding up to 13. We can subtract from 27 not only 13, but 12, 11, 10, 9, 8, and so on, down to 1, numbers we already know about. And then we can get to 27 itself. And then by adding to 27 the numbers 1 through 13, numbers we already know about, we can get up to 40, which is 27 plus 13. To get 41, we think of 40 plus 41, which is 81. And so our next weight will be 81. So we can get 41 by 81 minus all the others, and by subtracting 41, then subtracting 40, 39, 38, 37, and so on, down to 1, numbers we already know about, we can get up to 80, and then 81, and then by adding the numbers 1 through 40, numbers we already know about, we can get up to our total 121. So that's my solution. Instead of these numbers, which are 2 raised to a power, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, we see that the key to this challenge is actually multiplying by 3 each time. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. And to check that, the next one we would need is 121 plus 122, which is 243. And indeed, 81 times 3 is 243. So this puzzle at first sight may seem to have as its key powers of 2, but because we can put weights in both pans, the key to this puzzle is powers of 3. And so that's my solution to my counterweights challenge. Thank you for watching this solution video.